I came to science quite late. I was in industry. Yes, and a lot of PhD students I talk with, they say, should I pursue a career in science, or should I go to industry where the money is much better? It's true, money is much better. But there are good reasons to be in science, so we have no trouble finding people. And I think my experience shows that when I got to be ultimately as a director of a software house in the financial industry in the UK. I had a very high salary. I had 32 people reporting to me, most of them programmers. And believe me, I hated it. Yeah? And the problem was that I was the inspirator. I was inspiring other people, but nobody managed to inspire me, or very rarely, right? So maybe once a year I meet someone who does not talk about cars, for example, right? So at the tender age of 39, I went to my friend, the professor in Wageningen, and said, if you give me a chair and a table, I will join your lab. And 1 year later, I had a job at the university and became a research assistant, whatever it's called. And then, some 10 years later, I got my PhD. I was quite slow, actually. It's in 2015. And then 4 years later, I became an assistant professor at Tennessee. And since 1 month, I'm an associate professor. So now I can call myself a professor, for whatever that means. It's quite useful to have, actually. You don't realize it maybe, but when you're an associate professor, it's easier to get grants. Yeah, so that's where it starts, where you get the money. And why did they make me an associate professor? And again, it's money. Yeah, so during the lockdown, during COVID, in 2020, we moved back to the Netherlands. I was still employed by University of Tennessee, but I had a lot of time on my hands, so I started writing grants. So like an exercise. And we got two big grants. One for GNetwork. It's a software site, and I'm going to spend much of my time behind my laptop. So GNetwork, gnetwork.org, and this is a website for mouse genetics. Yeah, so we have mouse, but we also have rat in there, monkey, the fly, and all that. So we wrote a grant for GNetwork, and we got about $1.5 million for that. For 5 years. And this is pure for software development, nothing else, just to develop this service. And then, interestingly enough, I met some people at FOSDEM. I don't know, anyone of you know FOSDEM? Yeah? Yeah? I see in Jackie's hand, that's good. Francesco, know FOSDEM? This is my favorite conference. Yeah, so FOSDEM is a free and open source conference. It's every year organized in Brussels. You don't need to book anything, you just walk in. There are 80 tracks. I can show you the tracks. Let me see, so this is Saturday. Yeah, so these are the tracks. And about 6,000 people attended. And all the big names in open source software are there. Yeah, so it's a really, really good conference to go to. And obviously there's something for everyone, right? I mean, you can pick and choose. But there was one talk there in 2020 about the Hammerblade RISC-V Manicore, and I'm going to talk a little bit about RISC-V a bit later. But I met these people, and I said, shall we have a coffee? So we talked, and they said, well, we are working on hardware, but we're always looking for interactions, for collaborations. And I started talking about pengenomes, and they really lighted up. They said, oh, pengenomes, that's interesting. We've never heard of those, right? So we wrote a project together. And this is with Cornell University. And we got a $5 million grant from the National Science Foundation to create a 1 million core RISC-V supercomputer for pangenomics. Yeah, this computer does not exist at this point. Yeah, but the goal is in 3 to 5 years to actually have something. And it's built on this Manicore. So the Manicore is essentially 500 RISC-V cores on one die. Yeah, so it's a CPU with 500 cores. And unlike GPUs, in GPUs they have the disadvantage if you work with anyone programmed with GPUs yet? Yeah? So you know that all the GPU processors, they have to be in lockstep, right? They do the same instruction. Yeah, so this RISC-V many-core, all these CPUs, they can do different instructions. And for pangenomics, when you're traversing a graph, right? And I'm not allowed to talk about pangenomics, by the way. Oh, sorry, I forgot to say that. The organizers asked me not to talk about pangenomes. Because everyone else is talking about pangenomes. But that's why I'm talking about free software. Anyway, but there's some pangenomes here, obviously. So we created this grant, and so we have a $5 million grant to create this supercomputer. And obviously, with the supercomputer, we can do interesting things, and I'll talk a bit about that later. But this is why University of Tennessee awarded me associate professor. If you bring in your own money, no questions asked. I say, oh, he's good, he's fine. No. There's actually a famous quote by a dean, I cannot name him, but he said, I don't care whether this scientist has a lobotomy or not. As long as he's got a grant, he's fine. Right? So the key thing is science, even though we are obviously trying to do research, right, and we're driving for science, money is the key thing too, right, because it buys you independence. So if you can do that, that's key. Anyway, so let's go back to, that was the first line of my talk. I'm also an adjunct professor at Pwani University. And Jackie here was my master's student. Jackie, can you stand up? Yeah. So he's here. He did his master's on pangenomes. And my work is mostly creating software. So I'm a software writer. I'm a geek, right? I'm a programmer. So who here writes software? Hands up. Almost everyone? Almost everyone. So who here writes software that other people use? Oh, now it's much less. This is a fraction. Okay, so who here writes software that other people use that is hosted on GitHub? 4. Okay. Alex? Okay. Methods man. Okay, so and the last line is, oh my god, Pjotr's presenting in Emacs. So this was actually on Twitter, I think 4 years ago. There was a biology conference. Let me see. How does this work again? Okay, there we go. So, what I want to talk about, and whenever you're presenting, you cannot have the illusion that people learn a lot. Yeah. In fact, my wife, who's an expert trainer, she says that if one thing sticks, you've done great. Right? So I'm putting a few more goals here. So see if you can appreciate them. Free and open source software is crucial to bioinformatics. That's a point I'll drive home. Free software can help your career. Another point that I drive home, and I'm a case in point. I'm going to give you a tour of how I work. I'm not going to say that it's the way you should work. Maybe your work, the way you work is much better than mine. But after some 40 years of programming, this is how I do my stuff, right? So maybe you can learn something. I'm going to talk a little bit about programming languages, which is always a hot topic. And if I have the time, I will talk a little bit about this RISC-V thing. So, free and open source software is crucial to science. Who agrees? Majority. A careful majority. Okay, so, the one thing that is obvious is reproducibility, right? Yeah, so if you run a tool and it's a binary blob, right? You cannot see what's in there. And the vendor, could be Microsoft, says 1 year later, I'm going to upgrade this blob. Yeah, so you're going to go to from version 2.1 to 2.2, and your results change. What do you do? Yeah, so reproducibility is software is part of the reproducibility crisis we have. We call it a crisis, actually. Yeah, there's some papers about it. There's an estimate that if you look at biology papers, more than half of them turn out to be wrong later and turn out to be non-reproducible too, right? And software plays a role there. So free and open source software is also important for security, and I'll get to that in a point. But what is also important to me is that when I started as a programmer in the 80s, I was working in Windows. Well, initially in DOS, and then we got CP/M, and then we got Windows. And I was delivered to Microsoft. For the next 10 years, I was working with Microsoft tools only. And Microsoft, in its infinite wisdom, would upgrade the tools every year, and change the APIs. And something that was working before would not work anymore, right? And something that was not working before would start working. But the problem was that as a programmer, you were delivered to a vendor, right? So the vendor dictated the terms. And when I discovered Linux, which is around 1997, the first thing I did was start a mail server. But I discovered it, and I was going, oh, this is cool. I can see the code, right? I can fix it if there's a problem. And of course, for many people, that's a bit much because they think, oh no, I cannot fix Linux, right? Because it's huge. There's probably a billion lines of code by now. How do I fix stuff? But actually, you find you will fix stuff, when you get to use this stuff. So who's working on Linux right now here? Half? Okay. Who's on Windows? Yeah. Okay. Who's on OS X? No one programming OS X? Okay. One? Yeah. Okay. So all right. So one thing I've learned with Linux is also that it's long term. So the stuff I've learned, when I started in Linux in 1997, and what I learned in 2004 and what I learned in 2010, it's all still applicable. I mean, things do change sometimes, for example, the firewalling, they changed twice by now, but for good reason. But what I found is that whatever I learned, it sticks. And you can use it and reuse it and reuse it. It doesn't change that much. The other thing that's really important in open source software is the community. Yeah, so it's people like us. Yeah, and I've made many friends there. I met Eric Garrison through open source software. Right, he's coming on Wednesday. So Eric is now a colleague of mine at University of Tennessee. Yeah, so it's a community. Let's go back to reproducibility. So when you do an analysis, right, you start with the data, and then you have the software that you use to run the analysis, and then analysis itself, and that's a little bit fuzzy, okay? Ideally, what you would do is say, I'm going to capture the data, I'm going to compute the hash value of the data, right, as an input to my input of my final result. The tools can also be a hash, right? They can be fixed. The analysis bit, and Professor Carl Broman has a whole range of lectures on this. The analysis bit, if you do that in Excel, you're done. Forget it. Forget reproducibility. Yeah, because if you do something with the spreadsheet and you have not captured it, and you think, maybe even 2 weeks later, how did I do that, right? You have not done reproducible analysis. You have not done reproducible research. So what you need to do is write a program or a script, okay? And the script you can capture in Git, so it becomes a hash value, right? And then you have all the components to make it reproducible. But the software is part of that, right? And the software, if it's open source, it's hashable. If it's not open source, it gets tricky. So who's worried about security here? Privacy then, okay, try privacy. It's related, you see. Okay, so with security, if you cannot inspect something, can you trust it? Now, the marvelous thing, of course, is that we drive cars, right? So you drive a car, right? Do you trust it? Maybe. If you open the hood, you look in the engine compartment, right? And it's all messed up. There are wires everywhere. There's things sticking out. You still trust it? Yeah. If it was designed by someone, crazy, would you trust it? Right? Would you trust your life in a machine that goes 100 kilometers per hour? I don't know, right? So there's a trust issue when it comes to when something is not transparent. How did it get created? How did it get designed? We trust their vehicles because they're remarkably good, right? I mean, there's a lot of effort going in making them trustworthy. even though we still have car extents, right? So, when you talk about Docker containers, what is a Docker container? Yeah, it's a pretty opaque blob of software, right? Yes?
Something you cannot run if you are not root.
Sorry?
It's something you cannot run if you are not root on the machine.
Right. It's getting easier these days, but I agree. You know, I've tried to avoid Docker in my life. But yeah, the real problem as far as we are concerned is that you cannot really inspect it. I mean, you can open a Docker container, you can look inside it, but you don't really know how it was created because it's a binary. You know, it's a binary target. Yeah. So what you do when you create a Docker container is you say, you know. In Debian, you could say upget updates and then upget install, maybe say Python, right? What Python do you get? Do you know? And if you do modules or you use pip3, you know, to complete the Docker container, what is actually going in there, right? Can we trust it? Maybe. But I think, you know, is this important for bioinformatics? Yes. Because we deal with human data, right? Not all of us, but in principle, we should be targeting human data, right? So you have a privacy component, right? And then I have colleagues, you know, I'm not gonna name them here. They're my friends, you know, so it's not a big thing. But they are championing actually to take a Docker container and to bring it into a hospital to run the analysis with the Docker container, right? Get the results and then pull it out again. Yeah. So, and their idea is that this is protecting privacy. But you have to trust the Docker container. You know, that's a problem. And to see how important this is that it's not so. I mean, the Bitcoin people, and Bitcoin has been a bit in the news lately. But the Bitcoin people, they are very much aware of this issue of trust. They're really worried, and there's already been some breaches. You know, where the hardware is a problem, where the software is a problem from the ground up, right? So they want to have full transparency of everything, you know, to generate Bitcoin. Yeah, and they're driving that. They're into RISC-V, by the way. So, long-term sustainability. You know, that was the second point on that slide. One thing open source software is really good for is that we can go back in time. Right? So if you have done something 10 years ago, you can essentially rebuild the system that you had 10 years ago, right? And rerun the analysis. So it happens quite often that somebody comes to us and says, you know, I ran this analysis maybe only 2 months ago. But it could be, you know, 2 years ago for this publication, right? I did it for my publication. That's a famous word, publication. Can I rerun my analysis? You know, because the results I'm getting now are different. I'm going, well, you know, it's possible, but yeah, you have to do some effort. Yeah, but it's possible, and I think if we find, and we have actually the tools to do this, you can actually go back in time. You can create a time machine and rerun. At least redeploy the software as it was, rerun analysis, get the same results. Provided the tools are data ministry. Yeah. So if you look at the Burroughs-Wheeler aligner, BWA, every time you run it, it gives a different result, and then of course, you know, it's hard to reproduce. This is the wisdom of Hang Lee. So yeah, the open source community, I said, you know, consists of people like us, which is really important. We are geeks, right? We are not normal, believe me. It's not normal. Normal people don't look 10 hours a day at the screen. They don't. Well, maybe these days on social media, but not for programming, right? They don't take joy from programming. Yeah, joy from source. So we're not normal, right? But we have a community, and this community are much like us. Sadly, there's no support desk, right? That's a complaint by many people. Say, you know, when I have a problem with my software, I cannot go to a company and get the feedback that I require, right? It's true, you know. I'll talk a little bit about that too, because I have to support my software, and there are, I have difficult relationship with people who want support. Yeah, so there's no support desk. Companies do not like free software, but companies use free software, and they use it a lot, right? And we get very little recognition for that. Who knows that Apple's OS X is basically a free software underneath, right? Yes. Yeah. So they essentially took the equivalent of FreeBSD and built the whole infrastructure that they have today on top of that. It's an amazing feat. I didn't think they could do it at the time. They announced it, and I thought, well, this is going to take a long time. But they did it within 2 years. And not only that, but it was completely, they were able to run their older software too, which was on the older Macs. It's a real feat. Do they give back? Yes, they give back, actually. Yeah, but it's not on a large scale. Yeah, so Darwin, the whole OS X framework is closed source, it's proprietary, you cannot inspect. But they also created the client computer, CLang, and they put that in the public domain. So they give back, right? LLVM. They contributed a lot to LLVM. But I think we should keep arguing for free software, and I'll talk a little bit about that. And we should also replace proprietary software where we can. It's not always possible, right? But where we can. Question, what is free software? Yes?
Just to sort of digress on this, I was part of the free software movement in India. And one of the things we learned about free software was free as in freedom and not free beer.
Yeah.
That's how I would define it.
Have you got your career thanks to free software?
Yeah, more or less I would say, yeah.
Good. Good. Nice example. So what is free software? I think it's actually on the next slide, but what's the difference? Why is free software and open source software two different things? I mean, a lot of people talk about free and open source software, right? False. Actually, my slides are named that way. Free and open source software. Free software and free and open source software is slightly different from open source software, because open source software companies will do. They will say, okay, Microsoft has done it with Windows. They've said, okay, we'll make our software available as open source software. Everyone can look at it, everyone can scrutinize it, as long as you sign an NDA. So that's open source software. But free is important, because free means it can be deployed by anyone, anywhere, right? And if you look at reproducibility, that's a key feature, right? If you want to take a piece of software and you want to run it on a HPC, or you want to run it on your laptop, or you want to run it on your server, right? You need to be able to do that without having to ask questions, and that's the difference. If it's not free, it can be open source software, right? It ticks a few of the boxes, but you cannot just deploy it anywhere, right? So free software for reproducibility is actually quite key. Companies try to work around it, especially in cloud environments. They say, okay, you can run our software for free, right? But it's not free, because you cannot run it on your own computer in that case. So why should we put our software in the public domain and make it free? Right? Well, I've answered that question a few times now. Yeah, we need it for reproducibility. You need to allow people to run it. How does it help you or me? And this is a thing. I think when you're at your stage, many people are at your stage. As a PhD student, they wonder, should I put my software out there? So other people can see how bad I program. And there's some truth to that, right? I mean, we are all shy, but if you put it out there, you will find that some people may take an interest. That's good, right? Career-wise, I think it's quite important to do it. If I hire someone, I don't look at their publications. I never do. Trust me, I don't. I look at the software and the software they wrote. And if they have no software online, I'll ask them. I say, send me the software that you have. I'll have a look. And then I usually, very often people say, well, I wrote this software, and it's covered by an NDA, it's with a company, I'm not allowed to share it. And I say, well, it's your problem. You can trust me, right? I'm not going to share it, but that's where it stops. So career-wise, putting it out there helps. And one program is by Google. It's called the Google Summer of Code. Have you heard of that? Yes, some people have. Have you been on the Google Summer of Code?
No.
No.
Yeah, not so fortunate.
Yeah. Well, Jackie has been. I was a mentor for Jackie and Francesco here. He's been on Google Summer of Code. They should talk about it. But I've been. I was a what do you call it? An org admin. They call it officially, so an organization admin. And the idea of the Google Summer of Code is that Google frees up money. Today it's I think in the order of $2 million per year, which is nothing for them really. But what they do is they distribute the money across students. And the way it works is that when you have free software projects, you can create an organization. So I've been, for example, organizing for the Ruby project, BioRuby, or SciRuby, Scientific Ruby. As an org admin, you submit the proposal to Google, and they select the organizations that can participate. It's quite competitive. And then when the organization gets into the Google Summer of Code, the students can apply to participate in the organization. And when you participate in the organization, you can do some work for that organization, and Google pays you right over the summer. So it's they changed the rules recently. It's less money. I think also you don't have to be a student anymore, so that can work. But I think it's a great way because for people who have no experience in open source software development, this is a way to hone those skills over the summer. Yeah, so have a look at participating. For this year it's too late. I think it's already done. But for next year you can do that. Francesco, would you recommend it?
Yeah, absolutely.
Yeah.
Great way to get started in Pendulums.
Also in Pendulums. Okay, good. And Jackie, would you recommend it? Yes. Yeah. So what is bioinformatics? Let's go down to the basics. What is bioinformatics? How do you perceive bioinformatics? I mean, who of you calls yourself a bioinformatician? Not everyone. Okay. What are you? Biologist? Biologist, okay. Biomedical? Computer science? There we go. There's a few of those. All right. So bioinformatics, I actually wrote a Nature paper on this, or correspondence. What is bioinformatics? It's probably 70% data transformation and manual. Yeah, it's really depressing. And so most of the work that bioinformaticians do in general, and I'm talking about bioinformaticians worldwide, they're not writing much code, right? They're just preparing the data so it can be analyzed. This is a very depressing number, to be honest. Then, perhaps the rest of the time you spent installing the software, right? And dealing with dependencies. Anyone any issues with dependencies? Yeah? Anyone using Biocom now? Okay. I'll show an alternative. So, as a bioinformatician, how do you get to the point that you can actually do true science, right? And this is another question: is what is your career like? If you're a bioinformatician right now or you're a PhD student, what is your career prospect? What do you think you can be? Yeah, so that's one to think about. I'm sure you thought about it. Can you be a professor? Well, if you want to be a professor, you'll have to science, right? I mean, there's no shortcut, right? So you have to somehow get away from the data transformation, mangling, and you have to somehow get away from installing software. Yeah, so career, when I wrote that Nature piece, that was maybe 8 years ago, I was pretty depressed, because I thought, what is my future? Okay, I can be a postdoc. Maybe, so other people suggested I should become the head of a sequencing center or something like that, or the head of the HPC. Not exactly what I wanted, coming from industry. What career prospect do we have? I mean, it's getting better. There are now increasingly a number of people who are professors in bioinformatics, which is really positive, right? But Alex, yes, when you think about a career in bioinformatics, what do you suggest? Sorry?
I suggest to do this, but I give it a different name.
You give it a different name?
Yeah.
Okay.
That's just the title.
The title.
And it has nothing to do with the visual.
Yeah.
It's still bioinformatics, but if you call it differently, call yourself a pharmacist or I don't know.
Yeah. So, okay. Kind of answers the question. Change the title. Okay, yeah, so that's that. It's not that depressing anymore, I guess. So, having touched on all that, I'm going to give you a quick tour of how I work. Have you heard of the wavefront algorithm? Yeah, so Eric is joining us on Wednesday. He's going to talk about the wavefront, I have no doubt. It's a very fast method for sequence alignment. And in what we needed to do, what we needed to achieve was that we were doing variant polling using pendulums. So we were using the graph and then doing the variant polling. And we're doing it in human for the Human Pendulum Reference Consortium, and we're doing it in mouse and in rat. And turned out that the resulting variants have a lot of false positives. Yeah, so we needed to address that. We needed to find out what is actually happening. Why are we getting all these false positives? So Eric's idea was to take a VCF file, and where you have the reference allele, and then we have the alt alleles, right? And to realign them again against each other, yeah, to essentially to simplify the variants that were being called, and then to see how that worked out. So that's what we worked on for a bit. I'm going to show you that. So this is about genotyping and local realignment with short reads. And yeah, when it comes to the future, oh sorry, this is actually the different slide. When it talks about the future of pendulums, I'm not going to talk much about pendulums again, but I think there's going to be a very interesting work in genotyping. Yeah, I think we will do work on local realignment with short reads, which the previous speaker also talked about. Another thing that I would like to see is more support for metadata in the pendulum. So the pendulum is a graph structure in memory, right? And the current versions we have, they don't really support, metadata in a wider sense. So we can talk about that. Let's talk about Emacs for a bit. So I use Emacs. So this is my VCF lib library. These are let me see. So on GitHub we are, so you have the VCF lib project. I don't know if you've seen it. Have anyone worked with VCF lib? It's mostly for the VCF format. Do you know the VCF format? Yeah. It's ubiquitous. It's only 10 years old, but it's used everywhere. and it describes variants, right? So VCFlib is essentially a huge collection of tools that you can use on VCF files, so you can sort them and other transformations. Okay, and we started work on VCF Wave. So let me see if I can. How's the colors? Do I need to change the colors? Is it readable? Yeah. All right. So we have a VCF Wave, and it's a Markdown document which describes the tool, and it reduces complex alleles. Let me see if I can change that to visual line mode. That's not exciting. Yeah, I use a slightly wider screen when I'm writing this. So let me give an example. Yeah, so you have a VCF record here, which is on chromosome 4, position so much, right? And it has this reference allele, right? And then you get these ALTs, right? So essentially what it says is that for individual 1, or at least genotype 1, this longer stretch gets reduced to ACC. So there's effectively a deletion. You see that? Right? So we take that apart with VCF Wave, using the waveform aligner, right? And you end up with a set of alleles, yeah, where you have essentially the same starting point, so the same reference, but now it has reduced it to the C, right? So what actually happened is by realigning, these guys against each other, we actually can see, and you can see it by hand also, right? Here you can see that ACC and AC, they share the last C anyway, right? So it could be AC and A, right? And then you got ACA, right? So this shares the start of the other two, right? So you have one allele that is actually an A, and I don't know, did it show here? That's a C. Okay, well, maybe an inverse. Anyway, so we take it apart, and I'm not going to go into the details here. I'm just going to show you what I'm doing. So this is a Debian installed computer, right? You can see this Python is from 2019, right? March 2019, so it's quite old. So if I say Python -v, so this is Python 2, of course, 2.716, right? If I use Python 3, it's also quite old. It's from December 2019. So when you deal with tools on a standard distribution, they tend to be quite old, right? Yeah. Also, in this case, when we look at GCC, you see that the GCC on this Debian is 8.3, which is old. Yeah, so this was installed in 2019 on by the Debian project. It's actually pointing to 8. So to use newer tools, I mean, to write software, we want to use later tools, right? You don't want to use the old stuff, if you can avoid it. So what do you do? Conda?
You say a modern distribution, but
you can use a more modern distribution, correct? Yeah. But what I do, and I'm gonna show you some stuff because we use it for the Pangenome stuff too. Eric is also a fan. It's called Gnu Geeks. The Gnu Geeks project. Have you heard of Gnu Geeks? Yeah, Francisco is nodding warily. Yes. Yeah. So Gnu Geeks is a deterministic software deployment system. What do I mean with deterministic? It means that we can fully control the dependency graph. Right? The software installation itself is also a graph of dependencies. Yeah, and you want to be able to control it, and I'm going to show you what I do. And so, for example, you could say, so there's no Geeks standard on the system, so I'm going to use the Geeks that I, actually I'm going to create a profile. So now I have Geeks, package minus a Python, less. Yeah, so Geeks comes with Python, obviously, and a whole range of packages. You can see it's running Python 3.99, right? So the cursor's here. Yeah. Right, so let's install. So the Python we had on the Debian itself was 3.73, you know, from 2019. So we're gonna run Geeks shell Python. And now you can see that it's Python 3.99. Yeah, but it's, I mean, Geeks uses, because Geeks is deterministic, the software is reproducible. We don't actually store timestamps, so you end up with a timestamp that is 0. Yeah, that's why it says it's 9070, but you can ignore that. The main thing is that it's a modern Python 3.9, and it's running on, it was compiled with GCC 10, so it's more modern than the one from Debian. So what did I do? You know, I ran a Geek shell. So I said, you know, Geek shell Python, okay? And in the shell, I get the new Python. And all Geek shell does really at this stage is rewrite the path. So it points to the path which contains a Python, right? So, and it looks like this. Yeah, so there's a hash value here. And the hash value is for, in this case, unique for the profile, but there's also a hash value for the Python itself. Let me see. No. Python 3.9, sorry. So you can see that here, no, it's still in the profile. What happened here? Oh, forget it. But what is happening here is that all the software on Geeks is installed under a unique hash value. Okay? So to create Python, to create this particular version of Python, you take the source code for the Python itself, right? But not only that, you could also create the inputs, the other inputs that create the Python. Yeah, so we have other inputs. If I do an LDD, you can see there's a whole bunch of inputs, right? So the GNU C compiler was an input, of course, and there's a library there, right? And then glibc is an input. And all these inputs together, they create the hash value that is unique for this Python, right? Which means that you can have a unique Python on your machine, installed somewhere, and you can run it. Yeah, so I'm running it here now. Python 3.9. Okay, so now I'm gonna say import pandas. Anyone using pandas here? Right. So there's no pandas, but I didn't tell Geeks that I needed pandas, so I need to do that. So I'm gonna say exit. I'm gonna add Python pandas. Right. So now I say Python 3, and I say import pandas, and it works. Right. So we're in the shell now, but now I'm going to take it a little bit further. I'm going to say I want to create a container, so I'm going to say -c. So the shell, the standard shell, gives you the full Debian environment together with the Geeks environment, right? But now I'm going to create a container. In the container, I'm going to in the container will only be visible what I define has to be in the container. Okay, so I'm creating the container here. I need to create the privileges, sorry. I have trouble finding my mouse. There it is. My laptop rebooted when I plugged in the VGA. That was a nasty experience, actually. So I'm gonna tell the kernel to give me privileges to create a container, right? So now I'm creating. Now Geeks daemon is not running. Great. I need to start Geeks daemon. Geeks daemon, and I need to set the user group. Come on. So I need to start Geeks daemon so it starts responding to me for the shell, and there we go. Okay, so now I'm in a container. In this container, I only have Python and Python pandas, nothing else. Yes?
So again, does this mean you need to have sudo to run this?
To run the Geeks daemon, you need root privileges, yes. But that work, in HPC environments, we have workarounds. I mean, one thing you can do is use GNU Geeks to create a Docker container, and then turn it into Singularity, and then run it on the HPC.
Okay.
Yeah, these things you can do, but they work. I mean, the problem is that many HPCs, they don't allow you to get root privileges, right? So you need some workarounds. Anyway, ls is not in the container. Obviously, because I didn't define it, right? So I need to redo this. So I'm going to say core utils, which includes ls. Okay, now I've got ls. So you've got ls /gnu/store, right? These are the tools that are actually installed in more are not found. Yeah, right. Well, you can see that there are 74 tools installed in my container. Yeah, so even things like more do not exist. PI does not exist. Yeah, so this container is completely isolated from the rest of the system. And this may not seem very exciting, but actually, when you're a software developer, you want to make sure that all the dependencies that you need to build your project are there, right, and nothing else. So the great thing about a container, I use them all the time now, and this is not Docker container, this is a Geeks container, is that you cannot have anything bleeding out from the outside environment into your build system, right? And also, if you use something, you need to explicitly define to use it, otherwise it won't build. Yeah, so it's a very powerful tool, to create an environment where you can do stuff. So let me try and build VCFlib. What I did was on the command line, right? So I got Python and Python pandas. We have a bit more fancy. Geeks.scheme. So we have a little scheme file, and that rather than giving on the command line which packages I want to include, I have here a list of packages which I need to build VCFlib. And VCFlib is quite a complex project. It's got a lot of inputs, right? So, for example, we have the autoconfig system. We have CMake, which is implicitly defined here, CMake build system. The reason we have automake and autoconfig is because we also have HCSlib, and HCSlib is used for reading BAM files, for example. HCSlib wants OpenSSL these days, it wants curl these days. So we have GDB I use for development, obviously. ACF, we can define ACS-lib also from Geeks. We need Pandoc to create documentation. We need Perl to create documentation. We have Python tests, right? We have bindings against Python. We have Ruby to create Japan pages. We have Swiss Waterman. We have TabX, XC for compression, and zlib. So these are the inputs you need to build and deploy VCF-lib. Nothing more, nothing less, right? How does this work out with the coloring? Yeah, it's okay-ish. So now I'm in Emacs. In Emacs you can of course edit files, but you can also create a shell. And I'm going to start my geeks.scheme file in this shell. I have a little script for that. Let me see this command. So now I have the VCF-lib build system running in a container inside Emacs. Okay. So if you look at the GNU store, you can see there's 116 packages in there. Yeah, so that's the whole environment I need to do VCF-lib. So I'm gonna rebuild the thing. I'm gonna use CMake with in debug mode. Yeah, so and I'm gonna make, and this is gonna take a bit. I'm gonna build VCF-lib. This may distort the recording, by the way, because it's really taking all CPUs. So what about Emacs Powerboats? Have you used the Majid before? Majid? So this is Git inside Emacs, so I can say Majid. Right, so if you use Git, right, you can also do it in Emacs. But it has great functionality, for example, here to walk through Git Commits, right? Let me see, Eric put some commits in here 2 months ago, right? So I can visit that commit, and I can see what he actually changed. Yeah, so he changed these files. allele.cpp, and you can see that he's added these lines. Right, so Majid is a very powerful tool in Emacs. Usually when people leave Emacs for whatever reason, they say the main thing they regret is they cannot use Majid anymore. Well, they can, of course, but they're outside of Emacs. So Majid is one. So what else do you need for programming? Syntax highlighting, of course. Wave.cpp. Yeah, so syntax highlighting. I still see people writing code without syntax highlighting. Any one of you using coding without syntax highlighting? Oh dear. Reconsider. You know, it's so much nicer if you have even simple syntax highlighting. The Geek shell I'm showing you it's compiling at the moment. What else should the editor support? You know, for programming. So after 40 years of programming, do I need completion? No, I don't use completion. You know, some people do like it, but I don't. Do you use it for, what did I mean with code lookup? Oh, refactoring, I think it is. Yeah, so sometimes you get tools that help you with refactoring. Do you need an editor for that? Do you really want that? I don't know, I never use it. Emacs also has the towers of Hanoi. You need it for coding? Not really. It does everything, you know, everything you could want. So I showed the container contents already. I'm compiling in C++. Let's see what's happening. It's at 90%. My laptop is heating up to 92 degrees centigrade. The fan is not working yet. It goes at 100. Yeah, I'm gonna go through the modifying dependencies in a bit. Let's wait for this one. So it completed the coding, compiling the project. Let's change some code, right? So I'm gonna, in VCF Wave, I'm gonna change something. Let me see if I can refactor this. I've got some duplication here. So I'm gonna change that to here. Okay, let's do this. So, because I'm in Emacs, I can now hit F12 and it will rerun the same compilation command in the other window. And it says it has an error, right? So the error should not be there. Let me do it again. Okay, so build the target. Now I'm going to run the tests, right? So we got tests here, C test. Test passed and it's good. Okay, so I changed something, it recompiled, it relinked, and it ran the tests, right? So let me do it again. I'm going to say make -j 4, and when it completes, I'm going to run the tests, okay? So let me change something again. So I'm going to reintroduce the bug, hit F12. Yeah, so it found the bug quite quickly, that's good. I'm going to do it again. And now you can see it's taking quite a long time to link, right? I mean that took 5 seconds, and it didn't actually run the tests. So let me check what happened there. Oh, I forgot to put them in. T-test. So the test ran in 4 seconds. Now I was working on VCF Wave, so I can make the test run faster. So I'm gonna say only run the VCF Wave tests. Okay. So that's now 1 second. That's good. I'm gonna reintroduce the error. I'm gonna fix the error, and I'll wait to see how long this takes. Isn't that annoying? I mean, how many of you are programming in a language where you have to compile and then link and then run the tests, and at every step you go, why am I doing it like this? Right? So the first thing I said to Eric, I'm not going to work like this. There's no way I'm going to write code like this. You know, I don't want to be in this cycle all the time. So what I did is I created a Python binding. Python FFI, right? And the Python binding is quite simple. You know, it's I don't know if you've worked with PyBind before, PyBind 11, but and many languages have similar functionalities. But you can quite easily map C++ code against Python code. Okay, it's a little bit of work. You know, you need to sort it out. But once you have that, you can go to yeah, so I've got some code here that is written in Python, and what I did now for VCF Wave is I wrote the algorithms in Python first, and then when I was working in Python, I transpiled it to C++, you know, because that made Eric happy. But we could have stayed with the Python code, to be honest. All right, so I'm gonna run this code. Let me see if I can run it. Why is it double? Oh, it's Python 3. Oops. Okay, so I'm going to put it in the shell here. Yeah, so now essentially what I did is I ran VCF Wave, right? But I ran the Python version, and it was instant, right? So if I hit F12, it's instant. So if I go back to the code and I change something, let me just introduce a bug, right? I'm just going to put some rubbish in there. It gives me instant feedback. Yeah, and if I remove the bug, test pass. Okay. So one message here is that you can use higher level language, quote unquote, like Python, to do the software development, even if the backend has to be in C++. Yeah, so there's some. I mean, it's extra work to create the environment, but if you have to do a lot of work, it does definitely pays back because it's much nicer. And the other advantage of a language like Python is that it's easy to inspect things, right? So if I put a breakpoint in here, anyone work with the Python debugger? Right. So I'm gonna run the tests, but now I'm gonna invoke the debugger. So I'm going to say add the module pdb, right? pdb. No. Oh yeah, there you go. So I ran. Let me exit it again. So I ran the same commands, right? So I run Python 3. I run this script called realign.py, but I'm telling it to include the debugger, yeah, which comes with every Python. And I put a breakpoint in the code, right? So the breakpoint is here. Okay. So I run the code, and it drops me into the debugger at that breakpoint. So if I do list L, it shows you where I am. And now I can do run, which is R. And I do L again. It's actually at the end. Why didn't I do the breakpoint? Anyway, no matter. Let me do a simpler one. I think this is too complicated now. So I've written a little file, test.py, right? So here it says starting up. It says list is 10, 20, 30. I put a breakpoint in. Let me remove that. And you do something with the list, right? So you say Python 3 test.py, right? So all it does is print the list, okay? So now I'm going to put the breakpoint in, and I'm going to include the debugger, pdb, lists, and now it stopped at the breakpoint. I don't know why it skipped the other one. Maybe it put it in the wrong place. Yeah, so I'm still there. But the good thing about being in the Python debugger is that you can inspect variables, right? You could say display list, right? So it shows you the contents of the list. It can also say display I, which is the iterator, right? And say I is not defined. Well, that's correct because it's in the next line, right? So let's do next, which is run the next line command. You see, now it goes for I in list, right? And then it says print I, which is original source code. And now because I is changing, it goes from, it says it, the new value is 20 and the old value is 10. Yeah? So let me look at the list again. So that's what's happening here. We have the list here, 10, 20, 30, right? And for I in list, we print I. So we traverse the list, 10, 20, 30, and I, the value of I changes every time, and I can just track it. Yeah, because if I do next again, and next, right? You go through the loop, and at this stage it changed that value from I from 20 to 30. This is a very powerful feature. Yeah, so PDB is, debuggers you should use. If you're not using Python, you can use other debuggers. I use GDB a lot, the GNU debugger for C++. Yeah.
Maybe it's completely different from what you're studying. But one of the things about software development in a very professional environment is you have code reviews that collaborators. So, but in research, it's sort of an individual effort, or a solo effort most times.
Yeah.
So, I mean, are you going to sort of talk about it later or sort of?
Sorry?
I mean, are you going to talk back on that topic a bit later because?
Okay.
Yeah.
Cool. Yeah. Great. Yeah. So. Now in the next phase, I want to change some dependencies, yeah, because that's actually where Geeks shines. So in this case, in the Geeks.scheme file, right, we pull the HTSLib and tabix into the environment, right? But for development purposes, we also have tabix and HTSLib inside the source directory. You can see it on GitHub. Make it a bit bigger. In the contrib directory, we have tabix here. So tabix is included in the source code, right? And in tabix, HTSLib is included. Yeah, so these are Git submodules, we call them. Git. And the reason we are carrying, the source code of these things in VCFlib is that development of these projects also continues, right? So if you develop software and you use the tabix pp that is sitting on Debian or the tabix pp that is sitting on Geeks, you're working against an older version, right? So to make sure that we are up to date, we can also pull the source code into the Git repository and use that for development. And on HPC, this is quite critical because things like often these tools don't exist. Tabix pp is not installed by the administrators, so you need another way to get this information in. So how do you test that, right? And that's the key thing. So what I do is I say, okay, I'm going to make a new shell, but I'm going to remove HTSLib and I'm going to remove tabix. So in this shell, if you go GNU store HTSLib, you can see it exists, right? There's a binary there. So there's actually a binary called tabix, right? So it's running, right? So it's in the container. Tabix is installed, HTSLib is installed, and that's how we build this software. I'm going to leave the container now. I've commented out HTSLib as a dependency, and I've commented out tabix as a dependency, right? So I'm going to rerun the container, but without these dependencies. And I need that special line. This one. So now if I do /gnu/store tabix, there's no such file or directory anymore. So the container lacks the basic install of HTSLib and it lacks the basic install of tabix. Okay? So this means that my build environment, and the way we've done it is if it doesn't exist in the surrounding environment, it will take the source code from the Git submodule. Okay? So I need to remove everything, unfortunately. And now I say use CMake to create a new build environment. This is cool because you get hints here. It says checking for module HTSLib not found, tabix not found. Yeah, so and hopefully it picks it up now from the local environment. So if I say make for VCF wave, well, let's just make everything again. And actually what it did, if you see, it's building a HTSLib itself. See that? Build target HTSLib. So it's building it inside the directory inside VCFlib. Yeah, so I can build the whole thing, but it's going to take a while. So let's just try something else. In this container, the GCC I'm using is GCC 10. Yeah, which is at the moment the default for Geeks. What if we wanted to compile with GCC 11? What do we do? It's a one-liner. Yeah, I'm just going to tell Geeks that I want to use GCC 11. Okay? So now I'm going to rebuild the container again, so I have to exit, and I'm going to start the container with this long command. Okay, now I say GCC minus version. Whoa, we've got 11, right? So I go to builds directory, and then I do the CMaker thing again. There you go. And I start building, and it builds with GCC 11. Yeah, so I've not seen anything like this. You can inject essentially any version of a dependency into your build system, right? And it works. Yeah, so it will continue building. Okay, we did all that. So it's 20 past 5. Do you want to see how we are getting away from GitHub? What is the problem with GitHub? And now I'm going to prove that I'm a fanatic.
Now it's bought by Microsoft.
It's Microsoft, yes. So when GitHub started, and I had a very early account, and I was in the 10,000s. It was around 2009, I think, 2010, something like that. So not that long ago. And it was written in Ruby, which I thought cool because I do a lot of Ruby. It was great, you know. It was a two-man company, and they started in a garage, literally. Yeah, it's a famous American story, and you know, it's a great service. I mean, we all use it, right? So we know it does a lot of things really well. But there's a number of issues with GitHub, and I think one of in the free software community, one of our peeves is that GitHub itself is not free software. Yeah, so. And people think, well, it doesn't matter, you know. It's a public resource. It's free. We can use it, right? It's like Google Calendar, you know. We don't care what the source is like. It runs in my browser. My browser is safe, right? Cannot do anything. But actually, you know, the last question is quite important. You know, is it evil or not? And since I'm being paid by United States University, I have to be a bit careful with my words here. But the Americans are a little bit funny sometimes. Yeah, so GitHub, for example, blocks people who are coming from certain countries. Yeah. I mean, you can have an opinion about that. But they can do that. They have to do it because they're an American company. Does GitHub strive logging? I think yes. Yeah, their tooling is made in such a way that it's very hard to move away from GitHub. In fact, I'm proving it because I've been trying for years. I cannot get away from GitHub. The issue tracker. Yeah, so one of the primary features of GitHub, why people use it, is the issue tracker. I'm sure we've all used it. What is the problem with the issue tracker? There's a bunch. You know, I think one problem is that it's really hard to move your issues to a different system. Yeah, so there's a lock-in. They've made certain that you cannot simply transfer your issues from one place to another. There are some tools out there that can help, but it's not obvious. I also have trouble with the functionality of the issue tracker, yeah, because the problem is that everyone can post an issue. Yeah, so in my case, I have over 100 open source software projects I'm involved in. And anyone can post an issue. What does it mean? You know, if you have a project like Sambamba, we have a project Sambamba. It's used in every major sequencing center in the world today. How many issues do you think we get? Yeah, people say, I cannot install this thing on my computer. That's a fairly common complaint. Yes, it's also our responsibility to make the software available in such a way that it can be installed in your computer, right? But you're not paying me to do this. Yeah, so how do you respond nicely? It's a problem, you know, you can dealing with issues, certain issues, and people can get quite nasty. You know, I've seen issues, actually on VCF there's an issue somewhere that is quite nasty. This lady goes really bad. How do you respond to that? You can't really, you know, because it's a public place. So the issue tracker that GitHub has, the fundamental problem with the issue tracker that GitHub has is that anyone can post anything, right? And if you're running a software project, an open source project, and you're doing it in your time, you know, you want to have some control about who can post what. Yeah, if somebody posts something nasty, you want to be able to delete it, right? For example. Or maybe if you post something nasty in a moment of heat, right? You say, you bloodsucker, right? You cannot delete it. So what the solution we have is we create our own issue tracker, right? So let's see if I can find it. It's actually issue G network. Right, here we go. Yeah, so what we did is we created our own issue tracker. And if you look at a single issue, right, so let me look at this one. Add configuration to feature name. You can see it's a very simple issue tracker. And it's using a format we call gem text. And it's actually hosted on GitHub, so you know it's not all wrong. But we have a simple system which allows you to set tags, you know, like this is assigned to JGuard, right? You give a description, you can add links, all that stuff. But the important thing is that only people who are on the project can post issues. And of course you can submit a patch to our project and say, you know, I've got an issue, I've submitted a patch. So anyone can submit a patch. It can come in through the email, it can come in through the, you know, through the GitHub pull requests. But ultimately, we decide what goes into the tracker itself. And I think for us, it's very important. It doesn't work for every project, but for small projects like ours, it's quite good. So that's what we did. So we have our own issue tracker now, and it's actively being used. Yeah, so and it has some features you don't find on the GitHub issue tracker. I'm not going to go through all of that, but it's if you're interested, we can discuss. It has a pretty powerful search also. So that's one thing we did. Another thing we did is we created a continuous integration system. So is anyone using GitHub CI or Circle CI or Travis CI? No? Yeah? So the idea is that with these continuous integration systems is that when you can create a structure that when you submit a change to your source code, it will build the project automatically on GitHub, right? And then it will execute the tests, and if there's a problem with the tests, it will show you. So I mean, obviously you have not been exposed much to continuous integration apart from a few people, but using the GitHub CI is quite painful. I mean, we use it for PCF lib. Let me see. I can show you. PCF lib. So you can see at the top of the project at the README, you can see CI passing here, right? You've seen that before, correct? So if you click on CI passing, it shows you a number of runs that have happened when somebody pushed a commit. So I pushed a commit here. This is commit ED, D7, etc. If I click on it, it should show me that. Well, it says the run was 5.5 minutes and it was successful. Why doesn't it show the actual? Okay, yeah, this is the output of the project. Let me see if it. Anyway, you can traverse it yourself, but in principle you can see the whole, the software download, the build, and the test. And if there's any problem, you can see an output of the log that is done. So this is quite a useful system, because what works on your computer doesn't necessarily work on somebody else's computer, and you can use GitHub CI to validate whether it works in a more generic environment. Right? So that's useful. It's also a lock-in mechanism for GitHub, so we wrote our own. It only runs on Chromium, unfortunately. There we go. So we have our own CI, and you can see the GNetwork project failed on a commit, right? So let me check. So you can see what test failed. Yeah, so there's a test here that failed. And I can go back to the committer. I should be able to see who committed it, and then say, well, you let GNetwork 2 fail, fix it. So essentially, what we did is we created our own continuous integration system that when somebody pushes a commit to Git, it will rerun all the tests and it will show you what went wrong. But yeah, it's possible to do it yourself. That's what it amounts to. There's another thing that's evil about GitHub. Has anyone heard about the code completion feature of GitHub? Yeah, the software guy. So, what has Microsoft in its infinite wisdom done? They've created products where when you write software, you write code, right? It starts to predict the software that you are going to run. Yeah, so it uses an AI for that, and it does the prediction based on all the code that's on GitHub. Yeah, so my code that is on GitHub is being used by Microsoft to serve people to write bugs. My bugs. Right? But they haven't asked my permission. In fact, they have asked nobody's permission. And they are, so you can say, is this evil or not? Maybe not, because I put it in the public domain anyway, right? But I'm not very pleased, and I'm not the only one who's not very pleased about that. All right, so let's skip that. So we have half an hour left. Anyone want to talk about programming languages, or shall we just quit? Quit? All right, we had enough. Yeah.
We can talk about
RISC 5? Okay, so, and I'll keep that short. So we talk about open source software, right? And your open source software is running on non-open source hardware. What does that mean? Yeah, I mean, if you look at the Intel processor, it's got, I think at this stage, the newer processors have about 10 billion instructions on them, 10 billion. And so we're talking software in hardware, because these instruction sets, they are software in the end, right? But they're burned into hardware. There's in fact a full operating system on every Intel chip built since 2010 or so. You know that? Every CPU has a full operating system built in. And it's actually Andy Tannenbaum's Minix, was it? Minix, yeah, Minix. And Andy is not too damn well pleased about it. But he put it under free license, and so Intel took it. Yeah, so there's actually software running on your CPU that is running outside the operating system. So you install your nice free software, Linux or whatever, right, on your computer. And at the same time, there's software running there by Intel, which has nothing to do with your software, but it's monitoring all your actions. And actually can call both. Yeah, so all these CPUs, they actually can call Intel. they don't do it because people track that type of thing. But in principle, they do. They can do it, and they can go home. So this is not great, right? So one reason RISC-V is interesting to me and other people is that it's actually a free hardware platform. The architecture, the design of RISC-V is open source. It's out there. You can use it to create your own hardware. Yeah, so that's interesting in itself. Though the manufacturers can take liberties, right? So they can say, okay, I'm using RISC-V, but I'm going to expand the instruction set in my way. I'm going to put some extra software on it. But it's up to the manufacturer, right? But at least they don't have to be kind of open about it. And we can say, you know, this RISC-V processor is maybe not so free. In fact, one of the most important manufacturers, Sci-Fi, is at the moment not so free. They have some extensions. Okay, so that's one side of RISC-V, is that it's open hardware, you know, and it's a nice feature, to be honest. The other thing is that because it's open, it doesn't have licensing fees. Yeah, so if you can take ARM, for example, and create an ARM chip, you have to pay the licensing fees to the ARM company. Yeah, with RISC-V, this problem does not exist. So for research, it's great, yeah, because we're not tied to any type of licensing. What is more great about the RISC-V? It's running cool. Yes, it's a small chip, really small. It has a small instruction set. And if you look at Murphy's law, you know, so the law that said that chips will double in speed every year, right? We've plateaued on that. And the reason we plateaued on that is because of the heat dissipation. Yeah, the AMD, the Intel, the ARM is running cooler, but not by much. They have plateaued. You know, they have reached maximum speeds because we cannot get rid of the heat anymore at that scale. Yeah, so with RISC-V, the heat dissipation is much less, so the prospects for a faster chip is there. And they've already created 3 gigahertz RISC-Vs. Yeah, so that's going to be, even in the high performance computing area, they are very interested. And in fact, there's a project in Barcelona here with the Barcelona Supercomputing Center. It's funded by the EU, and it's to create a RISC-V supercomputer. And in the US, there's also a bunch of initiatives. But because it's an open platform, it's also in India, right? There's an Indian initiative, and Chinese are also on top of it. So RISC-V is already everywhere. It's ubiquitous, but people don't realize it yet. What's more interesting about RISC-V? So when we started when I started my presentation, I said that RISC-V can do instructions independently. And so if you look at the GPU, you have 2,000 cores or 4,000 cores. They all have to run the same instruction at the same time. Yeah, which originally made perfect sense for graphics, because when you go through a graphics map, right, a pixel map, you can do the same instruction for every row, so to speak. But we haven't really gone out of that, because if you look at any GPU today, they all run in lockstep. And they're pretty simple processors too. You know, these computational units, they're very simple. So RISC-V is a modern platform, very modern, and it's running cool, and every RISC-V can run its own instructions, right? So if you do for example, you write an algorithm to traverse a graph, every CPU can do its own thing in the graph, and it doesn't have to consider lockstep. And lockstep is very important because, you see examples like I think with GATK they try to use GPUs, right? And they use GPUs for variant calling. They use GPUs for the wavefront algorithm. Every time people say, oh, this is a great improvement. We got a 6 times speed improvement. 6 times, right? And I'm asking how many cores? 4,000. So there are bottlenecks that are not being addressed by these GPUs. So we think with the RISC-V we can do that. Okay, and the final thing about RISC-V, which I think is really exciting and very few people realize, is that it's a modular system. So these days we have more and more, like Apple with the M1 and the and 2, they have they call it SoC, right? SoC, system on a chip. You've seen that? And what it really means is you get all these, more and more of these, what used to be separate, electronic components. They all get to be burned on one chip. So the memory goes on there, the GPU goes on there, the CPUs are on there. Everything is localized on one die. Yeah, it's called a die. Now the RISC-V as a platform is also die-based, but within the die we can easily create compartments, and these compartments you can program yourself. So we're talking about creating modules that are essentially pieces of software, right? And then we can burn on the die as a system on a chip. And because we own the whole process, we can do it. So there was a very interesting talk. I was in New York at a hardware conference, my first hardware conference ever. And there was this guy talking about offloading garbage collection onto the RISC-V module, onto his RISC-V module. So garbage collection turns out to be quite an expensive thing. If you run a Python program, 20% of the resource on average is used for garbage collection. Yeah, just cleaning up behind it. So if you can offload that to a separate module, yeah, you gain room for the other CPUs. So that was one example. But I think if you think about running the wavefront algorithm, so like alignment stuff, if we can create a module that does simply the alignment, right? We can offload that task to the module and use the CPUs for other stuff at the same time. Think like that. And of course for encryption and all that, that's also coming. And the amazing thing is you can do it. We have FPGAs, which are programmable emulators, you could say, in hardware for RISC-V. And you can create these modules, try them on an FPGA, and if it works, you just burn it straight onto the SoC. And this future is around the corner. It's literally there. Anyway, that was RISC-V. And I think I'm done. Yeah, so if you want to reach us, we're on Matrix. Matrix is a free and open source software that replaces Slack, for example. It's a messaging platform, no more WhatsApp. No more Telegram, all these dark companies. So I'm on Matrix, Eric's on Matrix, the whole Pendulum effort is on Matrix. Who's on Matrix here, by the way? There must be a good bunch of you. Yeah. Only? Okay. Get on Matrix. You love it. So you can contact me on Matrix, right? And you can email me, obviously. Thank you.
Questions?
I think it was interactive.
Yeah.
Yeah, so I think we have to leave this place by 6:30.